Hello, and welcome to today's lecture on Value Stream Analysis, Identifying Value-Added versus Non-Value-Added Activities. A sub-module of the Define phase. Created by Lean Six Sigma Pro. A company dedicated to offering high-quality free online Lean Six Sigma training modules. In this sub-module, you will learn how to define a defect in Lean Six Sigma projects, how to identify the 8 types of waste in the value stream, how to distinguish between non-value-added and value-added activities, and how to create a value stream analysis. By the end of this video, the viewer will be able to list the 8 types of waste and provide examples. For each of the 8 types of waste, provide an example of a lean tool that eliminates or reduces the impact of that type of waste. Be able to classify an activity as value-added or non-value-added. Perform a value-added analysis. Together, Lean Six Sigma is a continuous improvement strategy that combines the DMAIC methodology and statistical analysis tools from Six Sigma and applies them towards eliminating the 8 types of waste, MUTA, identified in the value stream. On their own, Lean is about reducing the 8 types of waste in the value stream. Six Sigma reduces common cause variability process waste, also known as defects. Typically, a company will want to keep the two of these disciplines separate, as standalone practices. In my opinion, Lean Six Sigma provides the best possible strategy against the waste. Although, both can stand alone. Together, they look at all possible losses. Lean gains the use of applying statistical tools to analyze data and make educated conclusions based on facts and figures. While Six Sigma gains the use of looking at the entire value stream to ensure that they are going after the greatest losses in the plant. Taiki Ono, father of the Toyota production system, also known as lean manufacturing here in the States, defined the 7 types of waste in the value stream. Since then, an 8th defect type has been identified. Therefore, you may find some people refer to Lean as identifying 7 types of defects, whereas others recognize 8 types of defects. Taiki Ono, famous quotes, "Waste is anything other than the minimum amount of equipment, materials, parts, and work time which is absolutely essential to add value to the product or service." It is important to understand what he is saying in his quote, as it is the hallmark of lean manufacturing. Value stream is a term that refers to all of the individual steps in a process that are performed in order to produce a product or service the customer desires. Value-added steps, steps that convert raw materials into finished products. Non-value-added steps are steps that don't add any value to the process. The 8 types of waste are all non-value-added activities. This diagram details the basic process steps that occur in the value stream in order to convert a raw unit, the orange blinking dot, from raw ingredients into the finished product. The process is as follows: raw ingredients coming from one of the suppliers, A, B, or C, to the receiving dock, where the ingredients are either stored as inventory in the warehouse or delivered directly to the line for processing. During the processing step, the unit, if good, will go directly to packaging, and if defective, either to rework or waste. Units that make it to packaging are either shipped directly to the customer or are stored as inventory in the warehouse until demanded by the customer. We will look at this diagram again at the end of this training video. At that point you will be able to distinguish between the value-added and the non-value-added steps, and identify the types of defects that can occur at each step. Defining value-added versus non-value-added activities. Activities in a process can be classified into 3 main categories. These are: value-added activities, activities that transform the raw ingredients into the finished product, the activities that change the form, fit, or function of a product or service. These are activities the customer is willing to pay for. Business value-added activities. Activities that are essential to the process but does not transform raw ingredients into the finished product. Although they are essential to the process, the customer is not willing to pay for these activities. Non-value-added activities. Activities that don't transform raw ingredients into the finished product. They are the result of errors in the process. The customer is not willing to pay for these activities. Focus should be placed on eliminating these steps from the process. Lean classifies non-value activities into 8 categories. There are several acronyms to help assist the student in learning these. The one that I prefer to use is downtime. Applying the downtime acronym, the 8 types of waste are: defects, overproduction, waiting, non-utilized resources/talent, transportation, inventory, motion, excess processing. Defects are the easiest to recognize in any value stream. They are those that we typically think of when someone says they have process defects. A defect is a non-conforming unit. A unit that does not satisfy the customer's requirements. This includes product that will be scrapped, product that will be reworked, product that will be recalled, product that will be put on hold, etc. Defects are the result of poor process performance, lack of establishing good process controls. Therefore, this class is often solved using higher-level statistics, also called inferential statistics. This is the class that is commonly targeted in Six Sigma and Lean Six Sigma projects. Overproduction, producing more units in excess of the customer's demand, producing orders without demand, producing faster or earlier than needed by the upstream or downstream processes. The causes of overproduction can be many and varied. For example, long changeovers between processes. A business that is seasonal builds inventory levels based on previous year's orders, producing more units for a product that has a high historical scrap rate. Waiting, a unit of time where a process, person, or machine is suspended in an idle state due to circumstances outside of their control. For example, a process that has halted due to a process failure occurring upstream or downstream. In this example, the conveyor belts transporting the ice cream units to the next step in the process has halted due to a packaging error downstream. The heartbeat or drum rhythm of the process has stopped until the packaging error is cleared and is ready to handle the incoming units. At which point, the flow of the process will restart. Non-utilized resources/talent, the underutilized potential of a company's employees. This can be seen in many forms, from not promoting the talent from within the company, not exercising or listening to people's ideas, or not investing in employees' training and educational pursuits. In a lean culture, the potential of the workforce is unzipped, allowing for innovations, creativity, solutions, and advancements. Transportation, the unnecessary movement of materials, products, supplies, people, and information long distances in order to complete a task. A good example of this type of waste is storing inventory in an off-site storage facility. We have drawn a simple process flow to illustrate this point. In our example, raw ingredients are transported from the supplier, A, to the manufacturing site, B, which are then transported, C, to the off-site storage facility, D, where the inventory will be stored until needed for production. When needed, the ingredients are transported from the off-site storage facility, E, to the receiving dock, F. Once there, they are then transported to the production line, H. Typically, this type of waste is the direct result of high inventory levels, the category we will discuss next. Other causes are poor layout of machines, materials, supplies, and areas. This is often seen in manufacturing sites that are older and have been modified to fit the current production scheme. Inventory, excessive work in process, supplies, or materials than what is needed to satisfy the customer's demand. Excess inventory can result in the following: obsolete material, expired material, damaged product from environmental conditions, and high costs. Inventory results from supply chain issues where product is purchased on incorrect assumptions, overproduction, and transportation issues. Motion, excessive or repetitive movements of hands or feet to complete a task. This may also include the movement of materials, equipment, or supplies. This is often seen in manufacturing sites in old facilities with old processes that have had not undergone any automation and have not implemented lean. Such places typically lack POCA yokes, error proofing, or operator assisting devices. Motion is a type of waste targeted for changeover reduction projects because of the importance of reducing the time it takes to complete a task. Excess processing, pouring excessive energy into producing a unit that is of higher quality than the customer's expectations. In other words, it is performing additional work, process steps, than needed to complete a task. Examples include, making product within tighter dimensions than the customer's specifications, inspecting all units instead of a subset, providing the customer with an upgrade, data entry overload, writing down the same information on multiple forms. We have created a waste wheel of a food manufacturing process in order to illustrate the various relationships that exist between the 8 types of waste. During any one activity, the 8 types of waste can occur simultaneously, as a result of, as a precursor of, concurrently with, as a predecessor of, etc. The wheel consists of the 8 types of waste surrounding the value-added zone. In a normal process, value added consists of a relatively small percent of the total process time. In this illustration, we have 3 operators: receiving dock operator, orange icon, relief operator, red icon, and a filling operator, green icon. As the operators perform the steps in the process, we will display the types of waste that can occur at each step. The process consists of the following steps. 1. Raw ingredients are received at the shipping dock. 2. Raw ingredients are prepared for processing. 3. Raw ingredients are processed. 4. Product is filled into containers. 5. Product is packaged. 6. Product is prepared for shipping. The black window on the left displays the current step in the process. Identifying the non-value added activities, the 8 types of waste is critical to the survival of any company. For every unit of waste, the company loses money in the form of resources, materials, time, and eventually customer loyalty. Lean stops waste in its tracks. Now that we have presented the 8 types of waste and provided an example of how these 8 types of waste are linked, we will provide examples of lean tools that will assist in the elimination or reduction of the 8 types of waste. Eliminate or reduce waste type, defects. Lean Six Sigma is effective at eliminating or reducing defects, as its main intent is to focus on reducing variation that is inherent in the process. The greater the variation, the greater the number of units that exceed the upper and lower specifications, defects. Lean Six Sigma uses statistics to identify and quantify the important factors X's in the process that have an impact on the output Y. And, then applies solutions to eliminate or lessen the impact of that X or the interaction among multiple X's. The end result of a successful Lean Six Sigma project is decreased variation in the process and subsequently less defects. Statistical process control reduces the probability of producing defects by implementing statistical control charts that provide early warning signals when a process is trending out of control. Implementing statistical process control in real time, known as continuous monitoring, is a proactive measure. It provides clear indication of how the multiple X's are controlling the variation of the output Y at the current point in time. It is proactive because it warns the operator when a process is likely to yield defects. Therefore, the operator is armed with the knowledge to react when needed in order to eliminate the occurrence of defects. Total productive maintenance deep cleaning and defect tagging exercises eliminate defects on the equipment, which yields scrap and rework. During a deep clean exercise, operators perform a deep clean on the line, removing the oil, dirt, and clutter around the equipment, exposing hidden defects. While during a defect tagging exercise, the operator identifies and marks for improvement the critical defects that cause scrap and rework. Eliminating equipment defects decreases downtime related to minor stops, breakdowns, and process failures. The three main causes of rework and scrap. Eliminate overproduction by scheduling production based on a pull system instead of the traditional push system. In a pull system, production is scheduled based on the customer's demand and not on forecasting. Push system. Push systems are prone to overproduction because production levels are based on guesstimates in order to meet the customer's demands of the future. This is called a push system because units are pushed from upstream to downstream processes whether or not the downstream process is ready. Where in a pull system, the production schedule is based on a real-time customer order. In this system, there are two types of customers, internal and external. Production upstream is not produced until called for by the internal customer, downstream process. Internal customers call only for production when they have received the external customer order. Pull systems eliminates both overproduction and inventory. One-piece flow is an effective measure against overproduction because it limits batch sizes to small quantities. The concept of one-piece flow is to limit the batch size to one. In reality, it is producing what the customer wants, when the customer wants it, and not a unit more. This philosophy is part of a pull production system, where production flows are produced just in time and changeovers are optimized to single-minute exchange of dies, SMED, allowing for an easy transition between products. Reduce idle time by balancing production levels into smooth and consistent runs. In level loading, also known as heijunka in Japanese, the total volume from real-time customer orders are divided evenly into manageable daily production runs consisting of relatively the same number of units and product mix. This results in consistent and predictable production runs that eliminates idle time associated with irregular production schedules. In a heijunka environment, employees' schedules and activities are optimized for maximum efficiency. Eliminate waiting time by implementing TPM. One of the largest sources of idle time for equipment is due to equipment breakdowns, process failures, and minor stops. All three of which are due to the current state of the equipment. Total Productive Maintenance, TPM, is an equipment reliability improvement philosophy that focuses on restoring and maintaining equipment in basic state conditions, like new. This is accomplished through routine maintenance, daily cleaning, eliminating source of contamination, SOx, that cause defects, equipment improvements, and good lubrication practices. Eliminate or reduce the waste associated with non-utilized resources/talent by adopting a lean culture. In a lean culture, the front-line workers are empowered through training and skill building to implement improvements on the line and in the process. For example, in TPM, front-line workers are trained by the maintenance work group to take over daily equipment maintenance and care. Over time, they become qualified maintenance technicians. And, in Lean and Six Sigma, front-line workers are trained in Lean and Six Sigma tools and methodologies so they can fill the role of team member or eventually project leader. Over time, they can move through the belts to become a certified black belt. Eliminate or reduce the waste associated with transportation by implementing point-of-use storage, POUS. Eliminate unnecessary transportation of raw materials, equipment, and supplies by storing these items exactly where they are used in the workplace, the point of use. A common cause of transportation is the need to store inventory off-site due to overproduction. Eliminating overproduction and the amount of inventory on hand can be accomplished by lowering inventory levels. Oftentimes, a company will have high inventory levels due to long and excessive changeovers. Single-minute exchange of dies SMED focuses on removing non-value-added activities in the changeover process, allowing for quicker changeovers between products, which cuts the need for long production runs. Shorter production runs equals less inventory on hand and the need to store these items off-site. Eliminate or reduce inventory levels by implementing just-in-time processing. Just-in-time focuses on eliminating high inventory levels by producing only the absolute number of units needed in the time they are needed by the internal or external customer. Just-in-time processing requires a series of systems to be in place in order to be successful. One such system is called a Kanban. A Kanban is a card that signals to the user when to purchase supplies, materials, raw ingredients, etc. It is based on a frequency established specifically for that item. In order to reduce the waste of motion, we must first understand the path, distance, and the time it takes to complete the task. A spaghetti diagram is a visual representation of the movements made to complete a task. The idea is to calculate the time and distance, steps or hand movements, it takes to complete a task in order to identify the most efficient path. Eliminate or reduce excess processing by understanding the value stream. Value stream mapping is a visual representation of the flow of material and information through each phase of the process. It is used to analyze, identify, and mark for improvement steps in the process that are non-value added. It depicts both current state and the future state of the process post improvements. Eliminate or reduce excessive processing by implementing POCA-YOKES. POCA-YOKES are devices or controls designed to warn or prevent the user from completing an action in the wrong way. POCA-YOKES eliminate extra processing steps associated with reworking a unit that is defective due to operator error. Now that you have an understanding of value-added, business value-added, and non-value-added activities, know the 8 types of waste, and are armed with some lean tools to eliminate them in the process, we are ready to begin the value-added analysis simulation. In the remaining part of the video, we will focus on creating a value-added analysis in which we will look at each step of the process, noting the time it takes to complete each step and identify whether the step is value-added or non-value-added. During this simulation, we will point out some examples of lean tools that may be used to eliminate or reduce the step. Value-added versus non-value-added activities simulation. In the next several slides, we will look at the manufacturing of a chair from beginning to end. For each activity, we will list whether it is value added or non-value added. And, we will provide possible countermeasures to reduce the time to perform this activity. Value added analysis, mapping the value stream. An in-depth analysis of a process where each step in the process is identified as either value added or non-value added. Purpose, identification and elimination of waste points in the value stream. When performing a value-added analysis, complete the following steps with your team. 1. Create a process flow. 2. For each step of the process, identify if the step is either value-added or non-value-added. Note, you may also want to segregate the non-value-added from the business value-added. 3. List the amount of time it takes to complete each step of the process. The time it takes to complete a task can vary greatly depending on who is completing the step. If this is the case in point, use the average amount of time. During the observation exercise, for each operator observed, write down the time it takes to complete the task as well as the name of the operator. After the observation, analyze the data for max and min times, noting steps with the greatest amount of variation. These steps should be areas marked for future improvement. 4. Segregate each activity into value-added or non-value-added, sum the times for each group, and then calculate the percentage of non-value-added and value-added activities. 5. Create a Pareto chart of the non-value-added steps. Applying the 80-20 rule, identify the critical steps. 6. For each critical step, identify projects that will eliminate or significantly reduce the time it takes to complete the step. 7. Create the future process flow detailing the improvements made and time saved. Our process has been divided up into 3 main operations consisting of 21 steps in total. These 3 operations are as follows. 1. Painting operation. 2. Bottom chair assembly. 3. Chair assembly. In a value-added analysis, we look at all of the steps in the process. In this video, we will examine several of the steps in order to illustrate the use of the value-added analysis tool. For those steps that repeat, we will not show the analysis. Therefore, it should be assumed by the viewer that the same analysis steps were performed for all steps, not just the ones shown. Activity, obtaining supplies from inventory. Activity type, non-value added. Time, 45 minutes. Countermeasure, reduce time by implementing point-of-use storage, POUS. Obtaining supplies from inventory is a time-consuming non-value-added activity. It requires ordering parts out of the warehouse, waiting for warehouse attendant to gather the items out of inventory, picking the items up from the warehouse, or waiting to have the items delivered to the workstation, placing the items at the workstation, verifying the correct items are delivered to the workstation, and possibly removing packaging materials, as well as many other activities. The best countermeasure is to implement point-of-use storage. In point-of-use storage, the items are stored at the workstation in the correct quantities needed for the current production order. Point-of-use storage eliminates the following types of waste: inventory, motion, waiting, and transportation. As we go through each activity, we will place the activity on the value-added analysis chart underneath the correct heading. For instance, if the activity is value-added, it will go on the left-hand side underneath the value-added heading, and if it is non-value-added, it will go on the right-hand side underneath the non-value-added heading. Activity type, non-value-added. Time, 20 minutes. Countermeasure, reduce time by implementing single-minute exchange of die, SMED. Setup is a non-value-added activity. It takes time to set up tools, supplies, equipment, etc. After everything is put in its place, it then takes time to get the line up to nominal speed. Countermeasures include, implementing single-minute exchange of die, SMED, in order to identify the non-value-added activities and eliminate or reduce their impact. Improvements identified during a SMED activity are typically 5S, workplace efficiency, center lines, demarcations on equipment line, that are used for placements of conveyor belts or other equipment that requires alignment such as transition points, spacers, dials, equipment settings, etc. And, POCA yokes, error proofing, prevents incorrect setup. SMED reduces the following types of waste: motion, defects, waiting, and excess processing. Activity, painting units. Activity type, value added. Time, 65 minutes. Activity, painting units. Opportunity, reduce time by implementing POCA yokes, center lines, 5S. Painting units is a value-added activity because it changes raw ingredients into finished products. Even though it is a value-added step, if the step accounts for a large portion of the total process time, all of the sub-steps of this activity should be analyzed for possible improvement opportunities. For example, in order to make sure the part is produced right the first time every time, implement POCA yokes. Add center lines to the equipment and unit, if possible, to assist with accuracy of paint application, and 5S keep the workstation neat and orderly and void of clutter. POCA yokes, center lines, and 5S reduce the following types of waste: motion, defects, and excess processing. Activity, return supplies to supply platform. Activity type, non-value added but necessary. Time, 2 minutes. This is a non-value added step. However, it is necessary to store certain items such as tools, supplies, and materials close to the workplace for easy retrieval. This is an example of point-of-use storage. Storing items here takes approximately 2 minutes as opposed to the 45 minutes to store items in inventory/storage. Further improvement would be to eliminate the step of retrieving these items in the beginning of the process from inventory by keeping these supplies at the POUS in limited quantities based on a Kanban system. Activity, waiting for parts to dry. Activity type, non-value added. Time, 5 hours. Countermeasure, brainstorm ways to decrease drying time. This is the longest step in the process. Waiting is one of the 8 types of waste in Lean. Time waiting on parts, people, equipment, supplies, upstream and downstream processes. It is important to brainstorm possible ways to eliminate large time-consuming steps in the process such as this one in order to decrease the time it takes to manufacture parts. Activity, QA inspection of finished parts. Activity type, non-value added. Time, 25 minutes. Inspecting parts between steps is an example of excess processing. Inspections between steps is typically associated with a process that produces high defects. If your process produces high-quality parts, there is no need to perform quality inspections between steps. Unless this is mandated by FDA regulations or other regulatory bodies. Countermeasure, this is a good example of when to apply Lean or Lean Six Sigma in order to understand the multiple inputs that are leading to a low rolling throughput yield, RTY, and identify and applying solutions. The following types of waste are decreased by applying Lean Six Sigma: motion, defects, excess processing, and waiting. Activity, obtaining supplies from inventory. Activity type, non-value added. Time, 45 minutes. Countermeasure, reduce time by storing supplies, materials, and tools at the supply platform and applying a Kanban system for replenishment. Activity, QA inspection of finished product. Activity type, value added. Time, 20 minutes. Countermeasure, reduce time by implementing increased quality standards that reduces the number of units inspected from all to a subset. The final inspection of a finished product may or may not be considered value added. If the customer is willing to pay for this inspection, it is then considered value added even though it does not apply to the 3 criteria of value added activities. It is value added because the customer deems it important enough to want to pay for the inspection. Since this step can be either non-value added or value added depending on the individual customer, we will place this in the middle of our value added analysis chart. Now that we have reviewed each activity, we are ready to complete step 2. For each step of the process, identify if the step is either value added or non-value added. In our 21-step process, only 5 steps are value added. The remaining 16 steps are non-value added. Steps 3 and steps 4, calculating value added, non-value added, and total cycle time. We used Excel for our value added analysis. In an Excel datasheet, we listed all of the activities in sequential order, wrote down the time it takes to complete each activity in the first column, and placed an X in the corresponding NVA column 3 or VA columns 4. By setting up the datasheet in this manner, we were able to use the basic Excel function SUMIF. In this equation, B3 through B30 is the range of our activity times, C3 through C30 is the range of our non-value added times, and D3 through D30 is the range of our value added activities. The SUMIF statement searches either column C or D depending on the function to see if this column contains the criteria we are searching for, X. We repeated the same for the value added times. Our results: total non-value added cycle time is 569.5 minutes and value added time is 187.5 minutes. The total cycle time is 757 minutes. In order to calculate the percentage of cycle time that is taken up by non-value added activities, we divide 569.5 by 757, then multiply by 100. This equates to 75%. And, in order to calculate the percentage of value added activities, we divide 187.5 by 757 and then multiply by 100, which equals 25%. Of the 21-step process, there are 7 unique non-value added steps and 2 value added steps and 1 shared step, which is the final QA inspection of the finished product. For our example, we divided the time it takes to perform the QA inspection on finished product between the value added and non-value added times. Step 5. Create a Pareto chart of the non-value added steps. Applying the 80-20 rule, identify the critical steps. In our example, the top 3 non-value added activities that consume approximately 80% of the cycle time are: 1. Waiting for parts to dry. This activity alone consumes 53% of our total cycle time. 2. Obtaining supplies from inventory consumes another 16%, and 3. Setup consumes 11%. These are the steps that will be targeted for the first round of improvements. Step 6. For each critical step, identify projects that will eliminate or reduce the time it takes to complete. The first step of the process, obtaining supplies from inventory, is our second largest contributor. The team has targeted this step for elimination. A Kanban system will be established for the supply platform. This is 100% reduction of 45 minutes of non-value added activity. After going through the entire list of non-value added activities, the team has identified 4 projects. 1 Kanban system to eliminate storage of commonly used items. 2 SMED to reduce setup time. 3 Lean Six Sigma to reduce painting time. 4 Lean Six Sigma to reduce the sampling size from all to a subset for QA inspections occurring between steps and at final inspection. If these projects are completed successfully, the cycle time will be reduced from 757 minutes to 352 minutes, shaving off 405 minutes from the current cycle time. This is a 54% reduction. Therefore, the future process will allow them to produce 2 chairs in less time than it takes them to currently produce 1 chair. Step 7. Create the future process flow detailing the improvements made and time saved. The new process will have 3 steps removed, steps 1, step 8, and the final step 21. Also, the time to complete 8 different steps will be reduced. Part of 7 should include a graphical representation of both current and future state. Now that you have completed this submodule, you should be able to look at this map and identify the value-added and non-value-added steps, as well as be able to identify areas in the process where the 8 types of waste can occur. Let's try one together now. What types of waste can occur in the processing area? We see a non-value-added loop. This loop is as follows. Units are produced. Units that are not within the specification limits go to rework. If these units cannot be reworked, they go directly to scrap. The types of waste are: 1. Defects, the units that are not within specification. 2. Overproduction, to account for the units that are scrapped. 3. Waiting, downstream and upstream processes are waiting to restart normal production. 4. Transportation, possibly, depending on if we have to transport the rework and scrap to another location such as a holding area. 6. Motion, due to the scrap and rework, additional movements are required to handle the units which, if the units were in spec, would not normally occur. 7. Excess processing, to rework the units that are out of spec. As you can see, 6 out of the 7 types of waste identified by Taiki Ono's list are present in this area. This concludes our training video on value stream analysis, identifying value-added versus non-value-added activities. In this video, we showed you just a glimpse of the types of tools used in Lean to significantly reduce waste in the value stream and improve financial gains. We hope that you have enjoyed this video. Please join us on our YouTube channel at Lean Six Sigma Prowess, our Facebook page, Lean Six Sigma Prowess, or our website, which will go live January 1, 2016.